Question 1 and 2 are both about the conditions for spontaneity using Gibbs energy and Helmholtz energy as criterions. To answer these questions, we need to go over the second law. The second law says, in an isolated system, an entropy should increase for a spontaneous process. For a reversible process, the entropy does not change. If it's a non-isolated system, you need to take into account the system entropy and the surrounding entropy. They add together should increase. We showed that under special condition, one function includes both system and the surrounding, and that's Gibbs energy and Helmholtz energy. But you must remember the condition. For Gibbs energy, the condition is constant temperature, constant pressure. And so under this condition, the Gibbs energy decreases for a spontaneous process, and delta G equals 0 for reversible process. Under constant temperature, constant volume, it's the Helmholtz energy decrease as a criterion for spontaneity. If it's reversible, delta A equals 0. One more important property for Gibbs energy is that Gibbs energy change is a measure of the maximum non-expansion work. So with this in mind, we can answer these two questions. So the first question, delta A less than 0, the condition is constant temperature, constant volume. And if there's no non-expansion work. For delta G less than 0, the condition should be constant temperature and constant pressure. Question 3 asks you to calculate reaction Gibbs energy using two methods. In method 1, it asks you first to calculate reaction entropy, and then reaction enthalpy, and then reaction Gibbs energy using the equation delta G equals delta H minus T delta S. Okay? So that's method 1. And method 2, to calculate the standard reaction Gibbs energy using the formation Gibbs energy. So that's delta G is the formation Gibbs energy of the product minus formation Gibbs energy of the reactants. Alright, so this is method 1, this is method 2. Method 2 is number 4. So from 1 to 3 is using method 1. So first calculate the reaction entropy. Reaction entropy is calculated by the standard entropy of the product minus reactants. The answer is negative 386. Note that the entropy decrease is a negative number because the reaction gas phase forms liquid, entropy decrease. Okay, 2. Calculate the standard reaction enthalpy. So to calculate reaction enthalpy, we are going to use the formation enthalpy of the product minus reactant. So here is the formation enthalpy product minus reactants. And the answer is negative 636.62. And the negative sign indicates reaction is exothermic reaction. It releases heat. And now with these two, we can calculate reaction Gibbs energy. It's the delta H minus T delta S. And this is the first method to calculate reaction Gibbs energy. The answer is negative 521.5 kilojoule per mole. Now, when you use this equation, please keep in mind delta H is kilojoule, delta S is joule. Okay, when you calculate delta S, usually it's joule. You need to change to kilojoule also, so that they are consistent. Now, question 4 is ask you to calculate Gibbs energy using formation Gibbs energy. So here we use the formation Gibbs energy of product minus the formation energy Gibbs energy of the reactant. And those formation Gibbs energy can be found from this row. And the answer is negative 522 kilojoule per mole. And this number is consistent with the first method. Note that the result is a negative reaction Gibbs energy. And negative reaction Gibbs energy means the reaction Gibbs energy decrease. According to the second law, the reaction should be spontaneous under standard condition. Remember, when we calculate reaction entropy, and if reaction entropy is greater than 0, it's still not enough to predict whether reaction is spontaneous or not, because the second law says the reaction entropy, the total reaction entropy should be greater than 0. And therefore, the reaction entropy is not enough. You need to know the surrounding. Here, if you use Gibbs energy, then you don't need to think about the system surrounding. It already includes both. So if delta G is less than 0, then reaction must be spontaneous. The last question asks you to calculate the maximum non-expansion work. According to the second law, the maximum non-expansion work for a spontaneous process equal to the Gibbs energy change. And therefore, this question is to ask you to calculate delta G under the standard state. And the reaction is benzene and hydrogen combustion reactions. So comparison of these two reactions. So first, let's look at the benzene. The combustion of benzene is benzene reacts with oxygen, forms carbon dioxide and water. So how do you calculate delta G? Remember, we have two ways to calculate delta G. One is to use the formation Gibbs energy of product minus the formation Gibbs energy of the reactants. Okay. The other one is to use the reaction enthalpy minus temperature times reaction entropy. So let's see which one is available, the data. So benzene is C6H6, right? So we don't have these numbers. We only have the formation Gibbs energy. Therefore, we have to use the second method. So the delta G, right? The maximum non-expansion work should equal to the reaction Gibbs energy, which in this case is the formation Gibbs energy of product minus formation Gibbs energy of the reactants. So find those data, and the answer should be negative 3,202 kilojoule every mole of the reaction. Mole. In this case, you can say 1 mole benzene will generate 3,202 kilojoule energy to do useful work. Now notice that these questions also ask you based on per gram basis. Per gram. So what we have so far is per mole, and therefore we need a conversion factor, and that is the molar mass. Okay, 1 gram, actually 1 mole equals 78.18 gram, and so in this way it's per mole and the mole cancel, and that gives you per gram. So for benzene, every gram will produce 40.96 kilojoule non-expansion work. Similarly, we calculate the hydrogen fuel cell. Okay, so hydrogen will form water, oxygen. So you actually the formation Gibbs energy for oxygen is 0. Formation Gibbs energy of hydrogen also 0. So all you need is this one. The maximum non-expansion work for hydrogen fuel cell equals the standard reaction Gibbs energy, which is the formation Gibbs energy of the product minus reactants. The reactants are both zeros. The answer is negative 237.1 kilojoule per mole. Here per mole means per mole of hydrogen gas. And similarly, we need to change to per gram basis using molar mass of hydrogen. And the answer is negative 117.6 kilojoule per gram of hydrogen. On a per gram basis, nearly 3 times as much work can be extracted from oxidation of hydrogen than benzene.